Hello, so we are going to start chapter 7 today. This is about the sampling distribution. In the previous chapter, we learned the normal distribution, and before them, we learned like probability and averages and binomial distribution. So, up to this, like before this chapter, what we learned are more theoretical analysis of randomness, right? Or how to calculate mean, how to calculate probability, how to calculate conditional probability, variance, blah, blah, blah. So, uh, but what you may have realized it was that we do not think about data problem, right? It was purely like computation or theoretical properties, and like using Excel, right? And after this chapter, we will start the actual data techniques, estimation, inference, hypothesis testing, regression. Those are actual like applicable techniques based on the theory we learned in the previous chapters. And this chapter, the sampling distribution, is the bridge between them. Okay? So, in the end, ultimately, what we want is statistical inference. We would like to use the data to guess something about the randomness. Okay, from data, we would like to estimate, we would like to test. There are a lot of things we can do from the data, but to do that, we have to understand how the data were generated, how the data behave, right? So we are going to call the target, the object we would like to infer about as the parameters, right? So like in the previous chapters, what we learned is if we have a parameter, how the randomness is generated, how the mean and how the probability, how the variance are formulated based on the parameter, right? That's what we learned. Now we are going the other way. So we do not know parameter now, but we observe the realization of the randomness. That's the data. So from the data, we would like to go back, we would like to recover the parameters. To do that, in order to do that, we learned the other way. What would happen when there are parameters, and then based on the parameters, the data would look like this. So we can go the other way, and this chapter is more related to the data, not a simple distribution. Okay, so textbook has chapters about the sampling distribution, but usually I think it's really important. I think one of the most important chapters in this, like in general statistics, not just in this course, but usually often it's ignored or it's not taken seriously in most like statistics classes, and even my professors when I was a student, I wish they taught it more seriously. They taught it like explained it better to me. Okay, let me start. So the first warm-up question is pretty simple. So we are going to imagine like income distribution. Like as an economist, income distribution is the most common randomness, and we are going to randomly choose a person and ask about her annual income last year, how much she made in 2023. And we are going to assume that her annual income follows a normal distribution. So we write it as x follows normal distribution with parameters mu and sigma squared, mean and variance. Okay, so this is what we learned. Like in the previous chapter, we learned the properties of normal distribution, and so we know the normal distribution. But then in this setup, what is random? It is more fundamental question. Seemingly pretty obvious, but think about it. So we have x, we have like notation, like wiggle in normal and parameters. What is random? The answer is x. X is the only random thing in this notation. In some sense, it's pretty obvious. Okay, the reason is because the underlying, first, it's important to understand the underlying experiment because the experiment is what generates the randomness. So in this example, the experiment is to choose a random person. Choosing a random person, if you choose another person, then the other person would have a different annual income. So when we say random, that means if you happen to choose another experiment, if you repeat experiment, then the outcome would be different. That is the randomness, right? Like if you do experiment now and if you do experiment tomorrow, the results is in general can be different, then it is random. Okay, so from one experiment to another, if something is different, that is random. But the mean and the variance are not specific to an experiment. It is a property, something that governs all the experiments, underlying the experiments, right? Underlying the population. Right, so in some sense it is common, so everyone shares the same expectation, right? So expectation, because expectation is based on everyone. So in this sense, it's pretty obvious, right? I guess, I believe you choose the right answer in this question, simple question, and then it is important because you need to tell what is random, because when something is random, you can think about its probability distribution and you can compute the mean and the variance. Like, so when we apply what we learned, we have to have a random thing. So you have to tell what is random. If something is not random, then the probability distribution is so obvious or sometimes cannot be calculated. So we will you need to have keep this in mind. We need to check something is random or not. And similar question. Now, let's think about more realistic data. Say a researcher, an economist, conducted a survey of 1,000 people. So basically, it's just randomly choosing 1,000 people and ask their annual income. And the economist calculated the average annual income of those survey respondents. So we are going to denote X bar, the average annual income, right? X bar is the average annual income. Then what do you think? X bar is random or not? So there is nothing complicated in this question. It's pretty seemingly straightforward. First thing I suggest is you need to think about what is the underlying experiment. And imagine what would happen if you repeat another experiment, and if X bar stays the same, should be the same, then it is not random. But if it can change, then it is random. Okay? And in this example, the experiment is the survey of 1,000 people. So in the previous question, the experiment was choosing one person. But in this example, the underlying experiment is choosing 1,000 people. Just it is choosing a whole bunch of people together, right? I mean, they're independent, but a set of 1,000 people is one experiment. And then you get one outcome. X bar is the realization of the randomness. Okay? So then it is random because if you choose another set of 1,000 people, then their average could be different, right? If you happen to have, like, say, Elon Musk in your 1,000 survey respondents, then your average income would be much higher, right? So X bar is random because the 1,000 people you randomly chose can be different. And of course, the new set of 1,000 people will have different income distribution. They are going to have different average. So, in that sense, X bar is random. This is pretty obvious if I explain like this, but often it's very confusing. And still a lot of students, a lot of like even statisticians are confused about this idea. So okay, I'm going to set up so that is what we are going to study in this chapter. We are going to study because X bar is random. We are going to study its distribution. So we can think about its probability distribution, its mean, its variance. So that is what you're going to do. So let me set up the framework. We call the random sample, which is is a collection of observations, which is standard, and usually it's denoted by x subscript 1, x subscript 2, up to x subscript n. So you repeat the experiment n times, then you observe n number of observations. Okay, so here usually as before, lowercase n or uppercase n, alphabet n stands for the size of the random sample. So we collect like a n number of observations as one experiment, like this survey. In this survey, you observe 1,000 people at the same time. So exactly same situation. We assume that our data has n observations, and we kind of choose them as one experiment. Under the so for any data, if you treat them as a random sample, we are going to make two key assumptions. It's most fundamental assumptions in statistics. The first assumption is the identical distribution assumption. So all observations should have the same distribution, right? So if you ask the annual income, they must follow the same distribution. For example, what is wrong is like, for example, I ask annual income to one person, but to another person I ask weekly income. Of course, they are not the same thing. They are different distributions. Or I ask someone to someone I ask annual income in dollar, but to another person I ask income in say euro or like other currency or in $1,000. It's different. So we have to have all the observations must be identical, of identical nature. Okay, it's pretty obvious. This is usually not a big problem. But second assumption is more questionable and more important. It's the independence. We learned independence in chapter 2, and also we used independence in chapter 5 for binomial distribution. We assume that all observations are independent of each other. So first observation, if the first respondent's annual income has nothing to do with the second respondent's annual income, right? They are not a family, they are not like in their neighbors, and they do not compete each other, they don't work together. So we assume that all are independent. So these are the basic assumptions data must satisfy, and statistically we call that the random sample. Okay. So then we are going to, as I said, we are going to study how a random sample behaves, which is an extension of the previous chapter's theory. But the difference is, in our previous chapters, we think about one experiment, and one experiment generates one observation, and we repeat the experiment. Then we can learn, we learn the distribution of x. If you can repeat the experiment infinite times, then we know the true distribution of the random variable. That was our setup in the previous chapters. But now what I'm going to think about is the experiment of our interest is a random sampling, generating a random sample. That means already one experiment includes size n. N observations are generated from one experiment. And if you repeat the experiment another time, then you are going to have another set of n observations, right? Like it's like survey of 1,000 people. And then what is the outcome? Not outcome is not like just data themselves. The outcome is X bar. Like we are interested in the average, right? So one experiment has many observations, but in the end, we only think about one number, one outcome, that is the sample mean, sample average, right? Average of 1,000 people. Okay, that is what you're going to do. And when we say repeat the experiment, that means you are going to regenerate whole 1,000 numbers. And then by repeating those experiments, you can think about distribution of X bar. Or in our example, you can think about, say, one research center conducted a survey of 1,000 people. They report their own like annual average income. But there is another research center. They do their own survey of 1,000 people and independently, and they report their own like average income. So those two research centers are like may have like those two research centers would have different results, which is natural because the survey is random, but they already give like repetition. So you have two observations of average annual income. So what we imagine is we imagine there are infinite number of research centers and they do their own independent survey and they report their own average annual income, and then they would be different, the reports would be different, and then how would they behave? What would be their distribution? That is our setup. Okay, so we are expanding, generalizing our setup, like not just single random variable, but it is a bunch of random variable together, and repeat that together. Okay, so exactly this is what I said. If there are 100 research centers, that means the experiment was repeated 100 times. Okay, so then observations are not each single income, but the average outcome, average income from a survey. Okay, and then that is the sampling distribution. Exactly. We would like to learn the sampling distribution, and that means when I say I'd like to study the sampling distribution, basically that means what is the mean and variance of X bar, and what is the probability distribution of X bar, right? So if you open another research center yourself, and then without doing the survey, you can think about what is the expected annual income, what is the probability distribution of your result, right? So that's what you're going to do. But again, so when I explain this, it sounds pretty obvious, but it's confusing because of its name. So in chapter 3, X bar is a mean. We learned mean. X bar is a sample mean that is calculated from the data. We calculate the average from the data, right? You observe 1,000 income and you calculate their average. But I said it is random, so you can think about its mean. That means X bar is already a mean of data, but we are talking about its mean again. What is the difference? So it's mean of sample mean, right? This is confusing. This is where many people are confused. The point here is X bar is calculated from the data. It is what you calculate, but it is still random, right? Just the computation method is mean, right? But like the mean, when I say we are interested in its mean, then it is theoretical mean. If you could repeat, so this sample mean is from single income. Like you are calculating the average of single income, personal income, and calculate mean. But this mean, when I think about the mean of the mean, that is, if you repeat research center, if you repeat the survey, then what would be the mean? So first, on the line underlying experiments are different. And second, like this X bar is what you can calculate. But expected value, the mean of the sample mean is purely theoretical mean. So we are going to use theory to calculate this. So usual to reduce the confusion, we are going to use X bar. I'm going to call X bar as the sample average because that is what you actually calculate, and this is based on single observations, average of single observations. But when I say the mean of the mean, the sampling distribution's mean, that is expected value. I'm going to call this expectation or expected value because that is just hypothetical repetition of surveys. In practice, we cannot repeat survey, but theoretically we can do it. That's what we are going to do. Okay. So in the next in the next video, what I'm going to explain is we are going to study the sampling distribution, this expectation of surveys, but of course, expectation of surveys is related to the distribution of single single outcome, right? We distinguished single outcome experiment and multiple outcome experiment, but they are related to each other. So using those relationship, we can understand it better. That's what we are going to learn in the next video. Okay, thank you for watching. See you later.